Hi everyone. Previously, on our discussions on comparators, we discussed a very important problem that general comparator circuits face, that is, false triggering. So, when your comparator threshold voltage, input signal is very close to the comparator threshold voltage, in the presence of noise, your output can keep oscillating between V high and V low levels randomly. So, and this problem we called it as, uh, false triggering, and this occurs because your low to high threshold voltage will normally be equal to the high to low threshold voltage in conventional open loop comparators. To resolve this problem, we said we need to ensure that the low to high voltage is not equal to the high to low voltage. If you ensure this condition, then we get rid of the problem of false triggering. Now, these comparators, where the high to low voltage and low to high voltages will not be equal, are called comparators with hysteresis, or more popularly they are simply called as Schmitt triggers. Okay, in this lecture we will look at how to realize these Schmitt trigger circuits using op amps and resistors. In fact, the hope is that I'll try to very logically arrive at the Schmitt trigger circuits, and you should feel that the circuit realization makes complete sense. Now, these are the best circuit realizations that one can think of when one has to build a comparator with hysteresis. Okay, that's my goal. Let's see how far we accomplish it by the end of the lecture. So, before we go into the lecture, I'll just very briefly talk about, refresh your memory on what we discussed in the previous lecture. We said these comparators with hysteresis are called Schmitt triggers. The name Schmidt comes from the inventor of this circuit. It's a homage to him. And broadly there are two. You can classify Schmitt triggers into two types: a non-inverting Schmitt trigger or an inverting Schmitt trigger. A non-inverting Schmitt trigger is one where, as you keep increasing your input voltage, your output should either remain constant or it should also increase. Similarly, if you keep decreasing your input voltage, your output should either remain constant or it should also decrease. So if you look at the voltage transfer characteristics, the slope will be a huge positive value in the transition region and it will be zero outside. That is, I can broadly say that if you look at the transfer characteristics of a Schmitt trigger, a non-inverting Schmitt trigger, the slope will always satisfy this condition. That is, it's always greater than or equal to 0. Another interesting observation to make, which will be very useful when we are deriving the circuit realizations, is to see that the low to high threshold voltage will always be greater than the high to low threshold voltage. Okay, this is a very useful point. Just keep this in mind when we are deriving the circuit architectures for the Schmitt triggers. And generally, if you have a dual supply op amp, a dual supply circuit, then your low to high threshold voltage will usually be positive. So, and your high to low threshold voltage will be negative. Okay, so that is something to keep in mind. It's very useful. So even if I don't tell you what kind of Schmitt trigger it is, I just tell you that it's a Schmitt trigger and I give you the low to high and the high to low threshold voltages. By just looking at the values, by just looking at the low to high and the high to low threshold voltages, you can immediately say it's a non-inverting Schmitt trigger if it obeys this condition, where your low to high threshold voltage is greater than high to low, then it's a non-inverting Schmitt trigger. In the same way, we can define similar conditions for inverting Schmitt triggers. An inverting Schmitt trigger is one where, as I keep decreasing my input voltage, the output should either remain constant or it should also decrease. Okay, it should, as I'm increasing my input voltage, your output should decrease. And similarly, as if I'm decreasing my input voltage, the output should increase. Okay, the opposite of what was happening with non-inverting. Which means that I can express it in terms of slopes, as if you look at the voltage transfer characteristics, the slope should always be less than or equal to 0, right? So if you see in this region where the output is remaining constant as I'm decreasing my input, the slope is 0. In the transition region where I'm decreasing my input, but output is increasing. So slope is negative. Okay, it's a huge but a negative value, and it becomes 0 in this region as well. So that's an inverting Schmitt trigger. Now, the things to keep in mind for an inverting Schmitt trigger is that the high to low threshold voltage will always be greater than the low to high threshold voltage. So in the same way, even if I don't give what kind of a Schmitt trigger it is, and I just give you guys the high to low and the low to high threshold voltages, you should be able to say by just looking at those values, if it satisfies this condition, you say it's an inverting Schmitt trigger. And generally for a dual supply circuit, the high to low threshold voltage will be positive and the low to high threshold voltage will be negative. Okay, so this is all you just have to keep in mind. Now we will start discussing the circuit realizations for the inverting and non-inverting Schmitt triggers. I'll first start with inverting Schmitt trigger because it's much simpler to realize that. How should an inverting Schmitt trigger look like? The circuit realization should look like. So an inverting Schmitt trigger should have an inverting comparator kind of an architecture. So first we'll start with an inverting comparator. Inverting comparator is nothing but you just take a comparator, feed your input to the negative terminal and the threshold voltage to the positive input terminal. Okay, then you end up getting an inverting comparator. Right? So when your input exceeds, as I'm slowly decreasing my input, initially my input voltage, let's assume for theoretical analysis, I'm slowly increasing my input from a huge negative value. Okay, slowly the input is now increasing from a huge negative value. Okay, and your output at that point is positive. Right? It's an inverting comparator, so output will be plus Vsat. And the threshold voltage should be a high to low threshold voltage. Remember, this is how the inverting Schmitt trigger looks like. I'm slowly increasing my input from a huge negative value. So output is plus Vsat to begin with. When your input signal exceeds VHL, that is the high to low threshold voltage, your output should go to minus Vsat. So your output is plus Vsat right now, and you want the threshold voltage to be positive, right? That's your high to low threshold voltage. And we said for an inverting Schmitt trigger, it should be positive. Right? Low to high should be negative, high to low should be positive. So let's assume I'm connecting a positive voltage at the non-inverting terminal and see the characteristics of this circuit. Now the instant your input signal exceeds VHL, which is a positive voltage, it exceeds VHL, your output will go to minus Vsat. Now when your output goes to minus Vsat, what should happen to this comparator circuit? If I use the same comparator circuit and the same threshold voltage, this circuit is prone to false triggering, right? It's just this characteristic. I mean, if I immediately slightly decrease my input voltage, then the output will go to plus Vsat. So to build hysteresis, the instant your output goes to minus Vsat, I want the threshold also to change. Then I can achieve hysteresis. I want the threshold to become VLH, which is a negative voltage. Initially the threshold voltage was positive. The instant the transition happened, the instant the output has gone to plus Vsat or minus Vsat, I want the threshold voltage also to change. Now my threshold voltage is, let's assume I have somehow magically changed it, which is a negative voltage. I have changed it immediately at this point. When your output went to minus Vsat, I suddenly changed it to VLH, which is a negative voltage. Now even if I decrease my input slightly, the output will remain constant, because now the transition point happens at a negative voltage. This is 0 here, this is negative voltage. So now if I have to decrease my input voltage, only when my input becomes lower than VLH, which is a negative voltage, then your output will go to plus Vsat. So that's the idea behind it. So if I have to realize hysteresis, I should be able to change my threshold voltage on the fly. I should be able to change my threshold voltage with the output signal. The moment your output changes its polarity, I should be able to change the polarity of the threshold voltage as well. That's it. This is the idea that you have to get. If I can somehow realize this, if I can somehow change the threshold voltage with changing output, then I have built a comparator with hysteresis. That is, I have built a Schmitt trigger. Now let's make some observations. How do I realize that? Make some observations. When your output voltage is positive, when your output voltage is plus Vsat, the threshold voltage is supposed to be VHL, which is positive. When your output voltage becomes minus Vsat, you want the threshold voltage to be VLH, which is a negative voltage. And that's it. You have the hint there, right? How do I derive the threshold voltage? I can simply take the output and feed it back to a fraction of the output, feed it back to the non-inverting terminal. That's it. Because my threshold voltage also has the same polarity as the output, I can just directly take the output itself and some reduced version, or multiply it with some fraction, and then use it as the threshold voltage. So that's what I've shown here. So if I just take this circuit and a comparator, take its output, multiply it by some feedback factor beta, and feed it back to the non-inverting terminal. If I do this, what happens? The threshold voltage changes with the change in the output polarity. The moment your output goes to minus Vsat, your threshold becomes minus beta Vsat. The moment your output goes to plus Vsat, the threshold becomes plus beta Vsat. So it changes with the output, and that's what we need here. So if you look at the transfer characteristics here, the information is already there here itself. When your output is positive, the threshold voltage should be positive. When the output is negative, when the output has gone negative, the low to high threshold voltage should also be negative. The moment you realize this, then you can, if you are an engineer who is building the circuit from a first principles thinking, right? This is what you would do. All the information I need is there in this graph itself. I just need to derive my output voltage, the threshold voltage, from the output voltage itself directly. So that's how you get this structure, and normally the beta factor is realized using a resistive divider. I've just replaced beta by a resistive divider. I get an inverting Schmitt trigger. Okay, here the feedback factor beta is given by R2 by R1 plus R2. So this circuit is what we call an inverting Schmitt trigger. So now how to analyze this circuit? I have already made a YouTube video on how to analyze this circuit. So in this lecture, I'll just very quickly take you through the analysis again. It's very simple. Let's assume always when you're analyzing Schmitt trigger circuits, start from a huge negative voltage. If input is a huge negative voltage, output will be at plus Vsat. Okay, so your feedback factor will be plus beta Vsat. So your output voltage will be plus Vsat and your feedback factor will be plus beta Vsat, which is the same as your threshold voltage. So as I'm increasing my input voltage from a huge negative value, I'm increasing it and I'm slowly increasing it. At some point it will exceed plus beta Vsat. At that point your V minus will become greater than V plus. When V minus becomes greater than V plus, the output of your comparator will change its polarity. It will go from plus Vsat to minus Vsat. Right? Your differential input voltage becomes negative. Right? Your differential input voltage is nothing but what? V plus minus V minus. So your V minus becomes greater than V plus. So your output voltage will go to minus Vsat. The moment your output goes to minus Vsat, after that, even if I keep increasing my input voltage any further, the output will remain, it will stay put at minus beta Vsat. Okay, so what would have happened to this circuit? The threshold voltage would have become minus beta Vsat. That will be your V plus, and your V minus will be a positive voltage, will be greater than V plus will be V in, which is greater than plus beta Vsat, which means obviously it is V minus is still greater than V plus. So output will be at minus Vsat. Comfortably it will stay at minus Vsat. Okay, so now output is at minus Vsat, input voltage is at a huge positive voltage. Now I'll slowly start decreasing my input. As I slowly start decreasing my input, remember now the threshold voltage is minus beta Vsat. So because your threshold voltage is minus Vsat minus beta Vsat, as I keep decreasing my input voltage further and further and further, when your input voltage becomes smaller than minus beta Vsat, right? At that point, your negative, the inverting terminal voltage will be less than minus beta Vsat, and the non-inverting voltage is exactly equal to, non-inverting voltage is minus beta Vsat. So if you see, V minus becomes lower than V plus, so your V differential will become positive, your output will go to plus Vsat. Okay, the moment your output goes to plus Vsat, the threshold voltage will change. Your V plus will come to plus beta Vsat. But your V minus is a voltage which is smaller than minus beta Vsat. Okay, that's your input voltage itself. It's a huge negative value, it's smaller, and it is anyway smaller than, since it's negative to begin with, it will anyways be smaller than plus beta Vsat as well. So it will stay put at minus Vsat. Output will stay at minus Vsat. So that's how we have realized the inverting Schmitt trigger characteristics shown here. Okay, as you keep increasing your input, your threshold voltage will initially be positive. Suddenly, when your input changes from positive to negative, your output changes from positive to negative, when your input exceeds plus beta Vsat, your threshold voltage also changes to minus beta Vsat. Okay, so that's how we achieve it. This is the transfer characteristics of an inverting Schmitt trigger. So just a quick circuit. So if I feed, for example, where do we use one very useful application of Schmitt triggers is sine wave or triangular wave to square wave converters. I told you guys, whenever you're driving digital circuits, you need proper digital outputs. It should be either logic high and logic low, or plus Vsat and minus Vsat in a dual supply system. So if you feed any sinusoid signal which is varying like a ramp signal or a sinusoidal signal to a Schmitt trigger, you will get a 50% a square wave output at the output of the Schmitt trigger. Okay, and you can use a Schmitt trigger to generate that. So how does it work? So let's analyze the circuit. So it's given that we have a ramp signal, a slowly varying ramp signal, which is increasing in one cycle and it is decreasing in the other cycle. Okay, in one half of the cycle it is, a ramp signal is increasing, other half it is decreasing. So initially we'll assume that the ramp voltage starts from a huge negative value which is minus V peak. Okay, and then it is slowly increasing. So remember, when your input value is a huge negative value, your output will be plus beta Vsat. Okay, if your output is plus beta Vsat, only when your input exceeds plus beta Vsat, your output will change its polarity. Right, it's an inverting Schmitt trigger. So only when your input exceeds plus beta Vsat, your output will go to minus Vsat. And then it will remain constant. At this point, if you see, the input is increasing, reaching a peak value of V peak. Okay, it's greater than plus beta Vsat, so I can just say that you are in this region. If you are in this region where your input is greater than plus beta Vsat, your output is always equal to plus Vsat. So your output is always equal to plus Vsat. Now when I'm decreasing, until this region. Now when I'm after this point, your input starts decreasing. When your input starts decreasing, if you notice here, it goes lower than plus beta Vsat, but by then your threshold voltage would have changed to minus beta Vsat. So transition will not happen. The output will remain constant. That's what it's shown in the green curve here. Okay, as you're decreasing your input voltage, so I'm showing it on this graph here. Let's assume this is the point where it corresponds to V peak, the peak voltage of the input. Now if I'm decreasing my input voltage, the transition doesn't happen here. In fact, the transition happens at this point, at a negative voltage. So minus beta Vsat is at this point. So this is where the transition takes place, from minus Vsat to plus Vsat. And then the process repeats. So you keep decreasing it when the input signal is increasing, when it's going from, when the input signal is increasing, the threshold happens at a positive voltage. Okay, that's when the change in voltage, output voltage happens. And when the input voltage is decreasing, the thresholding happens at a negative voltage. The low to high threshold will be negative. So the transition will take place at a negative input voltage. So out in you give a triangular wave, at the output you get a square wave. And you can ask, see, generally when I'm testing students, we just test, asking them to find the duty cycle and all that. So generally, if your input signal is symmetric, right? If your input signal is symmetric and your threshold voltages are also symmetric around origin, right? Then the duty cycle will be 50%. If you apply a input signal which exhibits symmetry, right? Some kind of odd symmetry, then I can say that even if you don't follow what is odd symmetry, just draw a line along the zero line. Okay, the function should have some kind of symmetry around that point. So then we say that such functions, if you have such a function and your threshold voltages are plus minus are also symmetric around origin, if you look at this characteristic, right, there is some kind of symmetry that you can observe in this architecture. So if you have a characteristic like this, then we can expect 50% duty cycle at the output. Okay, so I'll solve problems on Schmitt triggers separately. So right now I just wanted you guys to understand the intuition behind this circuit architecture. How did we arrive at this? Okay, this is an inverting Schmitt trigger. Imagine a scientist who was first working on building Schmitt triggers. How would that scientist would have thought of it? So that was my reasoning. So all you need is a threshold voltage which changes with the output. Then I might as well derive it from the output itself. Just by putting a feedback network, I can derive it from the output itself. Okay, that's the logic behind an inverting Schmitt trigger. So the next circuit, before we go to the next circuit, this is one problem I've normally noticed when I was handling lab sessions for my students. So one thing I would normally notice is that when we give these assignments, usually when you build these circuits, we ask the students to plot the input waveform and the output waveform on an oscilloscope and see if it's actually acting like a Schmitt trigger. Many a times, one common mistake students often make is that they would apply an input voltage. Let's assume, I'll take some numbers. Let's assume plus minus VSAT equals plus minus 15 volts. And I'll assume beta is 1/3. So if beta is 1/3, the low to high and high to low threshold voltages will be at plus minus 5 volts. Okay, so this will be at plus 5 volts and this will be at minus 5 volts. Lot of times, suddenly students would be looking at the waveforms on an oscilloscope, expecting they would be feeding either a sinusoid or a triangular waveform, and they would be expecting to see a square wave at the output. Okay, oscillating between minus VSAT and plus VSAT. What they would observe instead is just a flat line. And that happens because a lot of times, again, students would often make, when they're generating the signal from a function generator, the input signal will be smaller than the threshold voltages itself. Okay, for a Schmitt trigger to work properly, the peak voltages of your input signal, modulus of that should be greater than mod of beta VSAT. You have to ensure this for an inverting Schmitt trigger. Otherwise, your output can be, if you look at this region where your input signal is lower than plus beta and minus beta VSAT, your output can either be in one of these two states. It can be either plus VSAT or minus VSAT. So your output will not change at all. So for your output to change, you have to satisfy this condition. Your input peak, your input has to be greater than beta VSAT. If for your Schmitt trigger circuit to work, this condition has to be satisfied. Okay, I'm just giving this example because I remember seeing this every year. I think for 3 to 4 years I was a lab instructor, and every year I would see this mistake again and again. And it's an interesting problem. I might ask you, what happens to this circuit if I feed, assuming that threshold voltages are plus minus 5 volts, and I feed a triangular waveform whose peak to peak voltage is minus 1 and plus 1 volts. It oscillates between minus 1 and plus 1, and I ask you to find out what is the frequency of the signal at the output of the Schmitt trigger. your answer should be 0 because it will be a flat line. It can be either plus Vsat or minus Vsat. If you apply some signal from some frequency f0 at the input, the output frequency will be 0 because the Schmitt trigger's output is not at all getting changed, right? Because your input signal is within this window. So where your output can remain at one of these two states. Okay, so that's something useful to keep in mind. So I just gave you an example. If I feed an input signal of, let's assume, plus minus 1 volt, some frequency, and I ask you the output frequency, the answer has to be 0. Okay, so that's another interesting thing. The next lecture, I'll talk about how to realize a non-inverting Schmitt trigger using op amps. Thank you.